Good morning, dear children. This is MP Gupta from Kendriya Vidyalaya, Lonavala. Today, I am going to discuss about the unit 8 of class 12th, D and F block elements. As we know, this chapter has allotted 5 marks question in board exam. In class 11th, I think you have already aware about the periodic table. So first we have to know about the position of D and F block elements in periodic table. Today just we want to start about the D block elements. So what is the position of D block elements in periodic table? D block elements are kept in between S and P block from group 3rd to group 12. Here it is P block element, these two S block element. The elements kept between S and P are known as D block element. There are 3 series in the D block element starting from 3rd period 3, 4th yani 4D series and 5th, that is 5D series. So there are 3 series of the D block elements, 3D, 4D and 5D, and these elements of the D block are in 3D series scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, zinc. In 4D series, yttrium, zirconium, niobium, molybdenum, technetium, ruthenium, rhodium, palladium, silver and cadmium. In 5D series, lanthanum, hafnium, tantalum, tungsten, rhenium, osmium, iridium, platinum, gold and mercury. So these are the elements of the D block. It is not necessary to learn all these elements, but at least 3D series are important to learn. That will be useful in the coordination chemistry also. Now, the properties and characteristic of D block element. First one, that is electronic configuration. First, the general electronic configuration of D block elements are n-1, D1 to 10, NS 1 to 2. Then if you see the electronic configuration of 3D series, we will find there are certain exceptional case. This will be in chromium and copper, scandium to scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper and zinc. So the electronic configuration for D block element for 3D series scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper and zinc. We will find that here 3D1 4s2, 3D2 4s2, 3D3 4s2, 3D5 4s1, 3D5 4s2, 3D6 4s2, 3D7 4s2, 3D8 4s2, here 3D10 4s1, then 3D10 4s2. Here is the exceptional case in case of chromium and copper. There is 3D5 4s1, here 3D10 4s1. This is due to the stability. This half filled is more stable than other configuration. This is completely filled and half filled is more stable. So instead of 3D9 4s2, it is 3D10 4s1, and here it is instead of 3D4 4s2, it is 3D5 4s1. And 5D, we will find here 4D1 5s2. So in place of 4, 3, it will be 4, in place of 5, it will be 5. So if we write the electronic configuration, we will find in the case of 12 group, that is zinc, this one, zinc, cadmium and mercury. In all these elements, we will find completely filled d orbital, 3d10 4s2. Now the question is asked, why these three elements are not considered as transition metals? So before discussing about the transition metal, we must know what are transition metals. The transition metals are the elements or metals having incomplete d orbital. In all these, we will find incomplete d orbital in their atomic state. Here it is completely filled, but we will find incomplete in most occurring oxidation state, like Cu plus 2. In case of Cu plus 2, it is 3D9 4s0. So the transition metals have incomplete d orbital in their atomic as are in their most occurring oxidation state. But in case of zinc, cadmium and mercury, it has completely filled orbital in atomic state and their most occurring oxidation state, that is Zn plus 2. It has 3D10 4s0. So it is not transition metal. The elements kept in the 12 group, like this zinc, cadmium and mercury, are not considered the transition metals. Second, atomic and ionic radii. In case of the transition metals, just here I have drawn here, in 3D, 4D and 5D, suppose this is 3D series, 4D and 5D series, the size of the 4D series elements is more than the 3D. But when go from 4D to 5D series, the size nearly similar. For example, zirconium and hafnium, this is the element of 3D series and 4D series, 4D and 5D series. This is 4D and this one is the 5D. The size of this one, these two are nearly same. Why? This is due to the fact lanthanide contraction. So before discussing about the similarity in the size, why the size differ, we have to know the lanthanide contraction. What is lanthanide contraction? As you know here, in these 5D, La, lanthanum, the 4f orbitals are filled before 5D. Due to the intervention of the 4f orbital before 5D, the effective nuclear charge, that is the shielding effect, increases. There is no decrease, there is no effect of the shielding effect. That's why effective nuclear charge increases and size decreases. And this size becomes generally similar to that of the 4D series due to the intervention of the 4f orbital. And the consequences of lanthanide contraction is that, like the question can be asked, why zirconium and hafnium are similar in chemical properties. Why they are similar in property? This is due to similar in the radii, and that is due to the lanthanide contraction. The next characteristic or property, that is the oxidation state. Oxidation state. The transition metal shows the variable oxidation states. This is due to the presence of unpaired electron in d orbital and available d orbital. The oxidation state of 3D series, this question is asked in board exam also. Write the oxidation state of 3D series element. We have to know, you have to learn the oxidation state of 3D series. The variable oxidation state of 3D series, scandium, titanium, vanadium, chromium, manganese, iron, nickel, cobalt, and zinc. Sorry, here is the Cu, cobalt, this will be nickel, scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, and zinc. The oxidation state of scandium is +3, only one oxidation state, titanium +2, +3, and +4, vanadium +2, +3, +4, +5, +2, +3, +4, +5, and manganese +2, +3, +4, +5, +6, and +7, iron +2, +3, +4, and +6. Here we see the variable oxidation state of 3D series element. The question is asked, which element of 3D series shows maximum oxidation state? The answer is clear. It is Mn, because it shows +2, +3, +4 up to +7. Question is why? Why Mn shows maximum variable oxidation state? This is due to the presence of maximum unpaired electron in d orbital. If you write the electronic configuration of Mn, you will find there are 3d5, that is 5 unpaired electron. Next characteristic, magnetic property. Or magnetic behavior. Transition metals are generally paramagnetic. The paramagnetism is due to the presence of unpaired electron. As we see the electronic configuration of the transition 3D series, 4D and 5D, there are the unpaired electron in d orbital. That's why they shows paramagnetic behavior. If that is completely filled, that becomes diamagnetic. For example, the question can be asked, how can you find the magnetic moment of particular ion or element of d block elements? For example, Mn, the atomic number is 25 and electronic configuration 3D 5 4s2. If you write the electronic configuration of 3d 5, the orbital 1, 2, 3, 4, 5, we will find the unpaired electron 5. Similarly, in case of iron 26, it is 3d6 4s2. 3d6, that is 1, 2, 3, 4, 5 orbitals, 1, 2, 3, 4, 5 and 6. Number of unpaired electron is 1, 2, 3 and 4. So, the magnetic moment is calculated by knowing the unpaired of electron by spin only formula, that is mu is equal to n plus 2, where n is number of unpaired electron. So, it can be calculated using this relation. So, n is here 5 in case of Mn, n is 4 in case of Q. Next one, the formation of colored ion. Transition metal forms the colored ion. This property again can be explained on the basis of electronic configuration. Why they, first question is asked, why the transition metal forms colored ion, or they are colored. This is due to the DD transition and presence of unpaired electron. If there is unpaired electron, there will be transition between the two sets of the orbital of D, and that is known as DD transition. So, first the answer will be due to the presence of unpaired electron and DD transition. because these metal or ion absorbs radiation in the visible region, then electrons are transited to the lower energy level to the higher, that is 3D, 2 set of the orbitals of d, and when it comes to its original level, it emits a radiation which also falls in the visible region, that is complementary color, which becomes the color of the ion or element. In case, for example, the question can be asked, which of the following are colored, whether it is colored or colorless, like scandium, first we have to know the electronic configuration. The atomic number 21, so it will be 3d2, 3d1, 4s2 for scandium plus 3. It is, there is loss of 3 electron, 2 from s orbital, 1 from s d orbital, it becomes 3d0, 4s0. If there is unpaired electron in d orbital, it is colored. If there is completely filled or no electron in d orbital, it is colorless. So it is colorless. In case of Cu plus Cu, electronic configuration 3d10, 4s1, Cu plus, it becomes 3d10, 4s0. In case of Cu2 plus, it becomes 3d9, 4s0. Is it clear to you? I think is that completely filled, unpaired. So these two are colorless, it is colored. Next characteristic, transition metal forms the complex ion. Why they form complex ion? The question can be asked, why they generally form complex ion. You will study the complex compound and complex ion in the next chapter, that is coordination compound. But there is the question, why they form the complex ion. Complex ion generally formed by the donation of the electron from the ligands to the metal ion, and generally the metal ions are transition and inner transition metals. This is due to the smaller size, higher nuclear charge and vacant d orbital. The answer will be smaller size, higher nuclear charge, and a vacant d orbital. Next one, the transition metals have high enthalpy of atomization. Why? Again reasoning question is asked, why transition metals have higher enthalpy of atomization? Enthalpy of atomization. Atomization means